expected value decision rule. I highly recommend that you watch the previous videos on Maximin, Maximax rules, at least prior to watching this video, because I'm going to use the same example that I used in the previous videos with a slight modification to accommodate expected value decision rules. So expected value decision rules are based on calculating the expected value. The expected value is denoted as E of X. You can either use a paren or a square bracket. Square bracket is more conventional than a paren, and it's generally found for random variables. Suppose I roll a six-sided die. The outcome of the die X is definitely random. The outcome could either be 1, 2, 3, 4, 5 or 6. The probability of the outcome is 1/6 across all outcomes, and the expectation is defined as the product of the probability times the outcome and sum the values of all these products, which is given by the sum over here. So according to the sum, the sum spans over I equals 1 up to 6. And the sum, we are summing elements where we find the product for each I. We take the probability of I and we multiply the outcome, which is nothing but I in this case. So I take the probability of the first outcome, multiply it by the value of the outcome. Probability of the second outcome, multiply it by the value of the second outcome, and so forth. And if I write it out, and this is what I'd get, 1/6 times 1 plus 2 plus ... plus 6. And using a little bit of algebra, you can find that the answer is 3.5. In other words, it's 3 or 4. Now, of course, if you roll a six-sided die, the outcome could never be 3.5, so we can approximate it to either 3 or 4. But although it is conventional that 3.5 be rounded to 4 rather than 3, but it could either be 3 or 4. It's a common issue that happens when it comes to student grading, and if the grade falls exactly in the middle, and we try to always round it up rather than rounding it below. But from a statistical standpoint or a mathematical standpoint, it could either be 3 or 4. So in this case, the expected value is a 3 or a 4. What it means is, if I roll a die over and over again, a six-sided die, on an average basis, I'm going to get a 3 or a 4. So if I roll a die 1,000 times, the average of all the 1,000 outcomes that I get, it will be 3 or 4. And that is the conclusion of expectation. So it is an average measure. It's nothing but the expected value of a particular random variable. In other words, the average behavior of a particular random variable. So I'm going to use the same example that I used in the previous videos. It's the bakery example, where the cost to make a cookie is 50 cents and the sale price of a cookie is $1.50, and the bakery only makes a dozen cookies at a time, and it plans to sell a dozen cookies and so forth. On any given day, a maximum of 5 dozen cookies can be sold, and the baker chooses to make up to a maximum of 4 dozen cookies. The objective is to find an optimal decision. We have iterated in the previous videos that the cost of a dozen cookies would be $6, revenue would be $9. There are 4 actions corresponding to the number of dozens of cookies the baker would choose to make, and there are 5 states. Those states correspond to the number of dozens of cookies that the bakery would sell. The key difference between this example or this rule and any of the previous rules is that in this case the states are not equiprobable. Now, of course, one can use the expected value rule for a case where they are equiprobable. There is nothing wrong with it. but I wanted to do an example where it is not equiprobable so that I can make the point quite clear about the use of probabilities, and which is why I'm assuming that the states are not equiprobable. But the problem here is if they are not equiprobable, then I have to say the probabilities of each of those states. Now, if they are equally likely, then every state, state 1 through state 5, would happen with a chance 1/5, which is 20% chance of happening. So we have to define the distribution of these states, and right here I'm defining the probability distribution of the states. This means that state 1 would happen 1/5 or 20% of the time. S2, the second state, would happen 40% of the time. S3 would happen 20% of the time. S4 would happen 10% of the time, and S5 would happen also 10% of the time. So that is what we call the discrete probability distribution. That is a term from probability theory. Now, on the top we have the reward matrix that we have seen several times before in the other videos. I'm not going to show you on how to create this video because I've gone over it in the previous videos. I believe it is a video on Maximax rule or Maximin rule. Please have a look into that particular video and you'll understand how to find the reward matrix. So now we have a reward matrix and we also have a probability distribution. The next step is to come up with the expected values. So I have rewritten the rewards matrix from the previous slide over here, and I've also written the state distribution. Now the objective is to find the expected values of reward for a given action. So if state 1 can happen 20% of the time, then there is a 20% chance that I would get a $3 reward. If state 2 happens 40% of the time, there is a 40% chance that I would get another $3 reward, and so forth. So what I'm going to do is I'm going to find, on an average basis, given these probabilities of states, what is the expected value of the reward. So all I have to do is use a formula. So the formula is I multiply the outcome by the probability of the outcome. The outcome here is the reward, and the $3 reward would happen with action 1, state 1, with a probability of 1/5. The second $3 reward would happen with a probability of 2/5. The third would happen with a probability of 1/5. Then as 3 times 1/10, and the last one would be 3 times 1/10. That will give a reward of 3. For the second action, if I am in second action, there are 5 possible rewards, and each of these rewards would happen with that probability. So the first reward of -3 would happen with a probability of 1/5. The second reward would happen with a probability of 2/5. The third reward would happen with a probability of 1/5. The fourth would happen with a probability of 1/10, and the last one would happen with a probability of 1/10. Which would give me -3/5, 0, 6/5. We add all that, I'll get +3/5, and that is 12/10, which is 6/5. The answer is 9/5. Now find the expected value for the third state. So -9 times 1/5 plus 0 times 2/5 plus 9 times 1/5 plus 9 times 1/10 plus 9 times 1/10. That's for the third action. Make space over here for the fourth one. I have 18 over 10, which is 9 over 5. And the last case, the expected value would be a negative 15. A reward of negative 15 would happen with a probability of 1 over 5. A reward of negative 6 would happen with a probability of 2 over 5. 3 times 1 over 5 plus 12 times 1 over 10 plus 12 times 1 over 10. If I add all together, I have minus 15 minus 12 plus 3 over 5 plus 24 over 10. Negative 15, negative 12 is negative 17 and negative 27 and positive 3. You'll have negative 24 over 5 plus 24 over 10, which is 12 over 5. You'd end up getting negative 12 over 5. Now we'd like to pick an action that gives us a maximum expected value. Clearly, here the maximum expected value is not offered by action 4. If we look at the second and the third actions, the maximum is 9 over 5, which is definitely less than 2. So we can't pick action 2 and we can't pick action 3. So the maximum of all the 4 actions is actually action 1. So action 1 is optimal according to expected value rule because it has the highest expected value. Therefore, the optimal decision is you make 1 dozen cookies. Because this statement over here should not be there, so let me just erase that. It's not part of this problem. Somehow it got carried away or carried over from the previous video. So according to the expected value rule, action 1 is optimal, and it is because it has the highest expected value. So the optimal decision is that I make 1 dozen cookies. If you recall from the Minimax rule, the optimal decision offered by Minimax is that we make 2 dozen cookies. But expected value rule, on the other hand, says make 1 dozen cookies. Now, I believe that this is the same answer that was given by the Maximin strategy, that we make 1 dozen cookies. So it always comes down to the researcher to make the final decision as to which decision rule to use and pursue the research from that on. The choice of a decision rule is usually dependent on the underlying process. If a distribution is well defined, for instance, we are more likely to use an expected value rule. But if a distribution is not well defined, it's best that we use the Minimax rule and so forth. So in summary, this is the expected value rule, and I hope you understood the expected value rules and all the other rules that we have covered so far. Thank you for watching.